Hi, my name is Ann Werda. This presentation is going to be looking at a science assessment system. We'll have an opportunity to talk a little bit about what assessment should look like in science, what a system could look like if we're measuring and monitoring growth and learning at multiple different intervals, and talk about how we can measure in an appropriate way for the students. So let's take a moment to think about what measuring learning in science should look like. Because we do see a lot of different kinds of assessments. I'll say that in my personal experience, many of the assessments that I review are predominantly recall, memorization, labeling parts of diagrams, and defining terms. And that's not predominantly what I observe when I observe those same teachers' classrooms. So I want to think about for a moment what doing science should look like. So if we were to just imagine if we were just to sneak into someone's classroom who's teaching science and someone who's an exemplary teacher, what would we stumble upon? Would we stumble upon something like this? Or maybe we'd walk in on a classroom and they would be doing something like this, or even something like this. So typically doing science has an idea in our head of what that looks like, right? But when we think about what measuring learning in science looks like, a lot of times it looks like this. So what we are seeing in terms of the ways that students are demonstrating their knowledge and communicating their learning, and the ways we're measuring and monitoring learning over time don't necessarily look the same as what we would think doing science looks like. And really, there's such a vast amount of information out there that it's hard for most science teachers to think about how can we possibly measure learning in such an expansive topic. Even if you already get as specialized as in the high school sciences, where we're looking at just introductory chemistry or just introductory biology, it's still a very large amount of material. So I think it's important for us to think for a little bit about why there's such a disconnect. Why does what doing science looks like, and when students are demonstrating their knowledge in the learning part of it, look so different than what we typically see as a science assessment? And I think there's three common reasons why there's such a disconnect here. I think one of them is very obviously the resources. In order to continue to do activities, it takes resources, and that means you've got to buy materials, you've got to find a way to store those materials, you've got to be able to distribute the materials to the students, you've got to have the ability to have the space to conduct different kinds of investigations. So approaching science from a let's do science as opposed to pen and paper science, sometimes there's a disconnect because of the resources that are available to us. Sometimes it has to do with the quantity of content that we're needing to cover. So when we think about those volumes and volumes of material that we need to cover, sometimes there's almost a race during this during the instructional interval to cover as much content as we possibly can. And this causes us to forego investigations, forego more complicated assessments for the multiple choice and quicker assessments because of the time. And I think it's important to think about prioritization within science, because even myself as a early science teacher coming from the professional science laboratories to the high school classroom, I was on a mission for my students to memorize as many different things as they possibly could. And my kids left my classroom reciting an impressive amount of scientific facts and understanding science to an intense depth that I was very proud of. But one of the things that we found over time with these students is that it didn't have the long-term effect in their memory as we were hoping. In other words, it was soon dumped in favor of other content that they memorized in other courses. So I had to take some time, and my whole department spend some time thinking about what was essential and what we wanted to emphasize over the course of the school year or the semester, so we could make sure that those really important learning concepts were addressed time and time again, and we really had an opportunity to impact learning in a very significant and long-lasting way in those specific items. So when we think about how we prioritize, one of the ways that Larry Ainsworth and Doug Reeves have both written about is to think about a three-step element. So the first element being that of endurance. So thinking about what would give the students value beyond a single test date. So this goes to something like naming the parts of a flower. If we're going to have the students do this on a middle school assessment, perhaps never talk about it again for the rest of the year, I would argue that that doesn't have endurance, and that may not be one of your high priority items that you're going to make sure that students learn and take with them out of that course. Whereas something like understanding the relationships between dependent and independent variables would become something that you address time and time again, and that would have endurance for the students, not only in that course, but perhaps in another class that they take subsequently in the sciences. Something like leverage is another great way to look at the prioritization of skills that you should measure. So thinking about what would have value in other disciplines, in other elements of your class when you come to different units, what's going to have applicability to multiple different units. This is something we consider having leverage. And finally, we talk about readiness for the next level of learning. So this is where we talk about, does this skill provide knowledge that will be important at the next level of instruction or in a career or at college level. When we have a student define a term like a restriction enzyme, for example, even if they plan to take subsequent science courses, there's an arguable effect that they may not need to have that memorized to be successful in chemistry or even AP biology. They could likely look that term up again and be successful even if they don't understand that term. However, something so elementary like understanding what a control group is, or being able to read a bar graph, these are what we would consider readiness for the next level of learning, because there's some level of expectation that, if a student is taking an upper level science class, that we have this expectation that they're able to read some basic graphs. So when we think about this vertical alignment between our courses, that really is an important element in the prioritization. Now, looking at these three elements, these are the big pieces that we want to include in our assessment systems. If we create assessment systems that measure the minutiae of our curriculum, we will get very overwhelmed and likely end up with meaningless 100-question assessments that we're giving on a very frequent basis that don't really have a whole lot of longevity, that don't really help students to work on some key skills that we're going to try to thread back and really make sure that they learn. I think the third reason why we often see a disconnect is the idea of traditional science. The traditional science classroom looked very different than what we see when we look in our science classrooms today. And I think that assessment in some aspects still looks a lot like assessment did many, many years ago. And one of the things that we can start to think about is how can we make assessment today look much more like the inquiry-based and the doing of science that we see in our classrooms. So let's think a little bit about a very traditional assessment and instructional method where you might pre-test them at the beginning of a unit. I'll use the example of when I used to teach my unit on gases. I would often ask the students, what do we know about gas, or what is a gas? And of course, we'd have a conversation about gases, and I'd learn some of their misconceptions. We'd engage in that unit then on gases with my understanding of their baseline knowledge, and I'd of course give a unit test at the end. Of course, once that test was done, we'd be done with gases and we'd go on to another unit, perhaps on metals, and that would continue throughout the entire semester. The problem with this is each unit really became an unrelated silo, and we couldn't really talk about longitudinal learning this way because each unit was unrelated to the next. In a assessment implementation model where we think about it as a longitudinal system where we're measuring and monitoring learning on key essential items over the course of multiple different units, we could potentially think about a system like in this particular graphic where there are 3 mirrored or comparable assessments measuring and monitoring learning on the same essential elements that we've decided are important from the gas unit, the metal unit, the non-metal unit, or whatever units you're teaching. We give a baseline to find out where our students are starting. That's assessment A. We'd analyze that data, we'd pivot, change what we plan to do based on the needs of the students and what our kids look like that year. We'd continue to teach, there'd be minor formatives, there'd probably be chapter tests. Assessment B would then look at how are students improving in those key skills that we want students to learn in the sciences, analyze that data and pivot, change what we plan to do based on the needs of the students, and of course Assessment C would be the summative or the final assessment where we would compare overall growth and learning in that particular area. So what we're doing is we're really assessing threads that run throughout the instructional interval. In a growth model, Assessment A becomes the baseline, Assessment B is like a midpoint check, and Assessment C is that final post-test or the final assessment. A lot of times people look at this graphic and they scratch their head and they say, well, is three the number of assessments we should be using? And I really don't believe so. I think this is a nice graphic. 3 looks very simple, but you're probably going to have multiple formatives, perhaps more than 3 in this particular cycle where you're measuring and monitoring learning, but you definitely need to have something between your pre and post test if you're monitoring growth over time. So if we were to put this into assessment types, Assessment A is a formative, Assessment B is a formative, you probably have other formatives, and of course Assessment C is your summative. So then when we start to think about the threads, the question is then, what are these threads? What do they look like? And how do I instruct in them and measure them? The threads are really your skills. When we talk about the content, we're talking about things that students will know and that are very specific to that course. So they're typically applicable even to only a single unit, maybe only a single text. So for example, dates, scientists who discovered things, particular diagrams, vocabulary, this kind of stuff tends to be at the recall level or the memorization level of cognitive demand. Skills, on the other hand, tend to be what the students are able to do, and this may be applicable to many units. Often they're transferable to future classes. These are things like solving problems, designing experiments, interpretation, analysis, making connections. In fact, this is really where you see those NGSS scientific and engineering practices coming to life in the part of students doing the science. I really do like this quote by Grant Wiggins because he talks about the skills that you develop throughout the instructional interval really being developing skills for this master culminating assessment. And the analogy he makes is that this assessment is much like the big game. So like a coach would help the athletes develop their skills and hone their skills in situations similar to the game, and then they lead up to this big upcoming game. The daily lessons that we have with our students help them to develop and practice these knowledge and skills so that when the upcoming game comes, we're able to have those skills honed in a way that we now can apply them in a new and a novel situation. So it's more than understanding a text or scientific concepts, or in a social studies class we would talk about a time period or other content. When we're talking about skills, we're really talking about skills that give the students the tools to be successful when faced with a new reading passage that they haven't read before, or a new series of texts, conflicting scientific viewpoints, or maybe it's a data set. So you're not having them analyze the exact same data that they looked at in class, but they're looking at a similar data set, maybe under a similar type of context, but it's new and they're applying those skills which they've learned in class. As we begin to have this conversation, I think a lot of teachers get very frustrated because content is something we're very passionate about. Many of us got involved in teaching science because we absolutely love science. And so when we start to talk about this, one of two things often comes up. Number one, teachers are afraid of losing content to teaching skills because we just don't have that much time. And so it seems like a natural next step is, okay, if we've got to change what we're teaching, then we're going to have to lose something. And the second thing is folks worry about watering down the content. And I really want to emphasize the fact that in my personal opinion, I don't believe that you have to abandon any content. In fact, you cannot teach skills without the content. The content is the vehicle through which you teach the students the skills. We can't teach the students to understand experimental design without understanding science in a particular subject area. So if they don't have a good understanding of the cell, they can't understand experimental design to learn about cell membranes. So it's really important that we say that this content is what gives the skills meaning. It's what gives the skills depth. But we also have to be strategic about our skills and make sure we're teaching them. I think the fault that myself included is that a lot of times we teach the content so vigorously and we don't teach the student the active application, the active making connections, and the skills that actually go with that content. So I think understanding task complexity will be really key to really understanding that differentiation in content and skills. When we think about Bloom's taxonomy or Webb's depth of knowledge, they're both great ways to talk about complexity. Webb has often said that there are hard things for kids to memorize and easy things to memorize, but at the end of the day, it's all level one. It's all memorization. And when you've learned that content, now you want to get up into the higher levels, like to understand the skills and the strategic thinking. That's really getting into the skill piece, which is the transferable piece. And the same thing when you look at Bloom's, that remember and understand level is really that lowest level of cognitive demand. And that's really where we get if we focus purely on the memorization of content. But it's once you start to apply that content or create something using that content knowledge, that's really when you get into the higher levels of cognitive demand. So the goal would be to try to get out of this level, but I know in sciences we do spend quite a bit of time there because there's just so much information. So we spend a lot of times having students do things that's at the lowest levels of cognitive demand. The goal would be then, once they've learned the term or understand the parts of the cell, what can they do then to get to that next analytical piece or the higher levels of cognitive demand? Let's look at a graphic of an assessment system to get an idea of how this might work. So for example, if we have several skills that have been selected in a course, let's imagine that we've selected the next generation scientific and engineering practices as common threads or skills that we're teaching over the course of many different units. So one unit might have content specific to it, but we notice that it showcases skills 1, 3, and 4 specifically. And maybe a different unit, though it might have, again, different content, the skill that's showcased are 2 and 3. So we've circled back to skill number 3 in both of these units, but we're showcasing different skills depending on what that content is. Knowing that the content is different in every unit, but the skills are what we're going to be able to measure and monitor over time for growth. And these skills are what we would consider the essential elements, these pieces that have leverage and readiness for the next level of learning. So if we were to baseline them in those important skills at the beginning of the instructional interval, we would be able to find out where students are starting in that particular set of skills. And of course, that post-test would show how much they've grown in those particular skills. Now, in order to talk about growth in those skills, this is really all you need. That is all you need in your assessment system. But then how do we make sure the students do well on that final test? How do we find out how they're learning throughout the course of our semester? How do we make sure that they're improving? So let's think about the Big Idea Unit A, one of our particular content units or chapters. We're showcasing skills 1, 3, and 4. So on our unit test, we should be able to measure how they're doing in those skills. We should be able to then on Unit B look at skills 2 and 3, and so on and so forth, developing an assessment system where over time we're looking at the improvement in those specific skills. Each one of these assessments can be formative and therefore direct us in how we can better teach those students in those specific skills. And some skills, like for example, the one represented by the heart here, might not be covered until late in the year, and that's okay for us not to measure them on the assessments until later in the year. Now, of course, there probably is some content memorization that's foundational and essential, like for example, definition of key terms. And it's not like that shouldn't be represented on a growth assessment, but it's just important to think about the spectrum of complexity. And you don't want your assessment to be 100% memorization. You want it to have a variety of questions at a variety of levels of cognitive demand. So really understanding question complexity will help you to understand if your assessment is doing that. So let's talk about how this would look in an assessment itself. This is an example of a science assessment, not uncommon from what we often will see. This is not obviously a skill-based assessment. This is another example, obviously not a skill-based. Both of these are examples of recall assessments that would be all at the very lowest level of cognitive demand. Not that this information isn't important for students, but it's also important to see the skill piece. Again, this is not a skill-based assessment. So here would be an example of a skill-based assessment. What we've got here is we've given them already the formula, so they're not having to memorize the formula, but we're asking for application. Here's a scenario that's different than what they've done in class before, and asking the student to determine what the independent variable is here. in analyzing this particular experiment. Then here's another example. This could be a comparable assessment that could be used at another point in time to compare student learning and their ability to implement those skills. So we're asking them to analyze this particular experiment. Again, they do need to know some content background on what density is in order to be able to determine which of these is the dependent and independent variable. They're also given the formula, so they have to do some calculations, and despite the fact that they don't have to memorize the formula, they still have to have some understanding of how to go about using that and applying it to be able to answer the questions that are on the assessment. So these particular assessments could be considered comparable for measuring learning over time in these skills. Here's another example of a skill-based assessment, and this is at the middle school level, and this is where we're really asking the student to design their own experiment. It gives them parameters for how they should go about doing such. It gives them some sample questions. Some folks who have looked at this have said would be very difficult to manage this. Perhaps giving them a shorter list of questions to choose from would be helpful, but that's what this teacher designed. And of course, then there would have to be a rubric as to how they executed the lab and did their write-up. And then, of course, that would show the teacher how they could allocate points and also make it clear to the student what they needed to do to be successful. I think it's important to say that this particular example could be repeated a second time with a different question to allow a teacher to measure growth in these several different skills. Well, thanks so much for listening about some examples of science assessment systems. I hope this is whetting your appetite for how you could potentially measure growth in your science class. If you're ready for more, don't forget to contact us, and we'd love to share more ideas with you and learn about how you're measuring growth in science learning.